Hello everyone, my name is Chiron. I'm a PhD student, second year in ANITI, and I'm working within the Calm chair within DIL. And I'm going to present my work, my current work, which is called LIST, Lipschitz Scaling Training for Robust and Calibrated Networks. So usually when you train a standard neural network, you obtain a network that is extremely accurate, or at least on easy problems. But you often lose two major properties for reliability, which are robustness and calibration. So these kind of networks, the standard networks, are usually brittle. A little perturbation, a little noise can alter the prediction. And they are often overconfident, which means they can't correctly quantify their uncertainty. Personally, within the Calm chair, we work on Lipschitz networks, which are a kind of network in which you constrain the sensitivity of the networks to be below a given value. And this kind of networks naturally are more robust. However, as I said, you have to constrain the value of the Lipschitz constant to up to a certain value, and it is hard to know by advance which value will yield a well accurate network and a well robust network. So this is a problem. And furthermore, the calibration properties haven't been explored yet, or not much. Which is also a problem because we have robust network, but we are uncertain about the calibration. Calibration, on the other hand, is another work, and a standard technique to calibrate neural networks is called temperature scaling, where you will just learn a single parameter, which is the temperature, and you will modify the entropy of the output distribution to yield a calibrated network. This is a really nice technique because it is easy to implement since you have only one parameter to optimize, but you need a calibration set. Furthermore, this is a post-hoc operation which is applied after training, meaning that you do not alter the robustness, neither the accuracy of the networks. So for the accuracy, this is nice, but for the robustness, it means that if the previous network isn't robust, it would stay not robust. The main idea I developed is to bridge the gap between these two notions, namely Lipschitz networks and temperature scaling. And what we found is that tuning T, tuning the temperature in temperature scaling is functionally equivalent to tuning the Lipschitz constant. We get similar calibration error on each case, meaning that we could maybe tune L the same way we tune T and obtain networks that are robust because they are Lipschitz and calibrated because we use the temperature. So we use this simple rule in our training, and we get networks which first will increase their Lipschitz constant to learn features, then robustify using the temperature feedback to get more robust, and in the meantime they are still calibrated. What we get is networks that are both robust and calibrated and more accurate than the static baseline counterparts, namely when you fix the Lipschitz constant to a given value. So our method removes the need to tune L by this proxy with the temperature. To conclude, our algorithm enables to train Lipschitz networks that are accurate, robust, and calibrated, which solves the trilemma. And you can ask me questions at the poster or afterwards. Thank you.